Okay, so today we're gonna really dive into something that I think is absolutely crucial for anyone who is building modern software, and really especially for anyone who is prepping for those like senior level technical interviews.
Yeah,
You know, where you really have to show that you understand architecture, right? And that's how microservices talk to each other.
absolutely.
Can feel overwhelming, right? Like there's so many different patterns and approaches.
Yeah.
So what we want to do today is kind of demystify two of the most fundamental ways that microservices communicate.
Hmm.
And those are request response and then asynchronous messaging, which usually involves queues.
Right.
And then we're going to kind of tie those together and look at how those patterns actually play out, you know, in like a typical workflow you might see.
Yeah.
So this is about like building that solid foundation,
Yeah.
you know, so you can walk into those technical discussions and you can really talk about distributed systems with confidence.
Yeah. And, for anyone aiming for those senior roles, understanding these communication patterns, it's more than just theoretical knowledge.
Right.
It's about, really understanding how to build those
Mm.
resilient and scalable systems.
Right.
And that's what interviews are really looking for.
Absolutely.
So, we're going to break down the essential concepts with practical examples.
Yeah.
So hopefully by the end of this, you'll feel, a bit more confident. You'll have that edge in those conversations.
All right. So let's start, I guess, with the most straightforward way to think about how services interact with each other. And that's the request response pattern.
Yeah.
And this one, I think, is probably the easiest one to wrap your head around, at least initially, right?
Right.
Because it's essentially, you know, one microservice sends a request to another and then it just sits there and waits for a response.
Yeah.
It's kind of like asking a direct question and you need that answer before you can move on.
Exactly. Yeah, it's that sort of blocking operation,
Yeah.
You're waiting for that reply before you can proceed.
Right. So maybe we could take like a common example of this in action.
Uh-huh.
Maybe something like you have a chart microservice and it needs to display like the current stock levels, you know, for products.
Yeah.
How would that work with a request response pattern?
Yeah, so in that scenario, you would have your chart microservice sending a check stock request
Okay.
to the inventory microservice.
Right.
And the chart service, makes that call
Mm-hmm.
and then essentially pauses execution, right? It's waiting for the inventory service to process that request and send back the stock level information.
Okay.
So it's a very, direct interaction.
It's very direct.
Back and forth.
Yeah, it is very tightly coupled, right?
Yeah, exactly.
Like that chart microservice is completely reliant on the inventory microservice being up and running
Absolutely.
and responding quickly, right? It's happening in real time.
Yeah, it is. Yeah.
It almost feels a little bit like, you know, those older monolithic systems where everything was just in one big application.
You could think of it that way. Yeah.
Right.
It's a sort of a simplified view of that kind of interaction.
Yeah. Okay. So this kind of direct coupling and this real-time nature, it makes it suitable for certain situations, right?
Yeah, definitely.
Like where would this be like the ideal pattern to use?
So if you need immediate information, if you think about something like validating user input,
Okay.
or you're adding an item to a shopping cart and you need to know, is this item actually available?
Right. Right.
So you need that information right away before you can proceed.
Right.
Or if the data you're requesting is critical for the very next step in a process, that's when request response really makes sense.
Okay.
It also works well, if you've got simple or well-defined interactions
Right.
where you're pretty confident you're going to get a quick and predictable response.
Right. Like you know what you're asking for and you know what you're going to get back.
Exactly. So it's got its place. It's not the solution for everything, but it's certainly very useful.
Okay. Now we should also mention that this request response can be either synchronous or asynchronous, right?
Yeah.
What's the distinction there beyond just that like immediate waiting aspect that we just talked about?
Yeah. So in a synchronous implementation, which is, we've been talking about with the chart and inventory example where you're waiting for that immediate response. What's happening is that calling service actually opens a network connection and keeps that connection open.
Right.
Waiting for the reply to come back.
Okay.
It's a blocking operation.
Yeah.
The calling thread is essentially stuck there until it gets that answer.
Okay. Yeah, that makes sense.
Yeah.
So what would like an asynchronous request response look like then? Because you're still, expecting a response, but you're not just sitting there twiddling your thumb.
Exactly. Yeah. So in asynchronous request response, the sender initiates the request, but it doesn't block, it might get immediate acknowledgement.
Like, hey, I got your message.
Yeah,
Oh,
exactly. I've got your request. I'll get back to you later. but the actual response itself will arrive later. And that might be through a callback mechanism or by the sender polling for, checking back periodically, hey, is that response ready yet?
Okay.
And that can improve the responsiveness of the calling service because it can go on and do other things.
Right. It's not just blocked waiting.
Yeah, exactly.
Okay, that makes sense.
Yeah.
So let's move on to another key pattern. And this is asynchronous communication, but specifically using message queues.
Yeah.
And this one sounds like it's really all about decoupling services, right?
It is. Yeah, that's the core idea with asynchronous communication using message queues. The service that's sending the request, or I guess more accurately, the message, right? Because it's not really a request in the same way.
Right. It's not expecting an immediate response.
Yeah, exactly. It doesn't wait for any immediate reply. It just puts the message onto a queue.
Okay.
And then it just goes on about its business.
Right.
The receiving service, then, whenever it has the resources and it's ready, it'll pull that message off the queue and process it.
Okay, so can you give us like a concrete example of this in like a microservices context?
Yeah, absolutely.
Like how would this play out?
So let's imagine you've got an order processor microservice.
Okay.
And it needs to tell the warehouse microservice to reserve stock once an order is placed. Now, instead of doing that direct request response, what happens is the order processor sends a reserve stock message to a designated queue.
Oh, right.
And the warehouse service, when it's ready, when it's got the resources free, it consumes that message from the queue, performs the stock reservation.
Okay.
And then, crucially, it would typically send a stock reserved confirmation back to another queue that the order processor is listening to.
So there's often like two queues involved here, right? One for the initial message and then one for like the eventual response.
Right, exactly. You've got this two-queue system, or sometimes you might use a single queue with correlation IDs.
Okay.
But the point is, you're achieving this decoupling between the order processor and the warehouse.
Right.
The order processor doesn't need to know if the warehouse is even online.
Right.
At the time it sends the message.
It just drops it in the queue and walks away.
Exactly. It just sits there safely in the queue until the warehouse is ready to handle it.
Right.
Similarly, the warehouse doesn't need to directly, reach back to the order processor.
Right.
It just posts its message on a queue where the order processor will eventually pick it up.
Okay, so this decoupling sounds like a huge win in terms of like building more resilient systems, right?
Absolutely.
Like if the warehouse is temporarily down for some reason, orders can still be placed and then the stock reservation will just happen like whenever the warehouse comes back online.
Exactly. Yeah. This asynchronous pattern inherently leads to improved resilience.
Right.
If one service, has a temporary outage, messages just accumulate in the queue and processing can resume as soon as that service recovers.
It's also, I imagine, more scalable, right?
It is, yeah.
Because each service can just kind of process those messages at its own pace.
Right. Each one can work independently.
Right.
It's not held up by the other
Right.
or overwhelming the other.
And the queue itself is kind of acting as a buffer, right?
It is, yeah. It's a built-in buffer.
So if there's like a sudden spike in traffic, it can handle that more gracefully.
Exactly. Yeah, it can absorb those peaks and prevent things from falling over.
Okay. So you mentioned earlier that the receiving microservice needs a way to get the response back to the original sender in these asynchronous scenarios.
Right.
We talked about dedicated queues, but are there other ways to do that?
Yeah, absolutely.
Especially, if you don't want to have like a million queues floating around.
Yeah, that's a valid concern. You don't want to just proliferate queues everywhere.
Right.
So while using separate queues is common, another approach is to actually include metadata in the initial message, like a reply to queue identifier or a correlation ID.
Okay.
And then when the receiving service processes that message, it can use that information to route the response back to the right place.
Right, right.
Or allow the original sender to correlate the response with its initial request.
Okay.
Match them up, basically.
And you also touched on this earlier, but the challenge of like linking responses back to the original requests.
Yeah.
Especially if like some time has passed or the requesting service has, multiple instances running.
Yeah, that can get tricky.
How do you typically keep track of all that?
So because the response might not come back to the exact same instance of the requesting service that sent the initial message, a common solution is to store some state related to that original request in a persistent data store like a database.
Okay.
So you give the initial request a unique ID and include that ID in the asynchronous message.
Okay.
And then when the response comes back, it also contains that ID. So any instance of the requesting service can retrieve the associated state and continue processing.
So it's kind of like a lookup table?
Yeah, you could think of it that way, yeah.
Okay, so we've covered these two fundamental ways that microservices communicate. Now, in the real world, a single user action often involves like multiple microservices working together.
Right.
So how do these patterns actually come together when we need to achieve like a larger business goal?
Yeah.
That's where the idea of orchestrating these services comes in,
It
right?
is, yeah. A lot of business processes require the coordinated actions of
Yeah.
several different microservices.
Right.
So let's go back to our order processor example.
Okay.
Let's say it needs to first make sure that the requested stock is available and reserved before it proceeds to actually take payment
Right.
from the customer.
So it's not just one back and forth, right? There's like
Yeah.
a sequence of interactions that needs to happen.
Exactly. So in this kind of sequential orchestration, the order processor would first send a reserve stock request to the warehouse microservice.
Right.
And as we discussed before, this could be a synchronous request-response interaction
Okay.
where the order processor is waiting for confirmation that the stock has actually been reserved.
Okay.
Only after it receives that stock reserve confirmation does it then move on to the next step
Right.
and send a take payment request to the payment microservice.
So in this case, we're kind of seeing how that request response pattern is like the underlying communication mechanism,
Yep.
but it's happening within this broader orchestrated workflow, right?
Right.
Like the order processor is kind of like the conductor,
Right.
making sure each service does its part in the right order.
Yeah, it's coordinating the whole process.
Right, and making sure that the necessary conditions are met before moving on to the next step.
Yeah.
This strict sequencing feels really important for maintaining the integrity of the business logic.
It is, yeah.
Right, like not charging someone for something that's out of stock.
Exactly. You want to avoid those kinds of inconsistencies.
Right.
So yeah, this orchestration pattern makes sure that those dependencies are respected.
Now, we've kind of stumbled upon a nuanced point here
Yeah.
about the terminology. The subtle difference between using the words commands versus requests.
Right.
Especially when we're talking about this asynchronous communication.
Yeah.
Can you shed some light on that distinction and why it might matter?
Sure. So, you'll hear some architects and developers using the term command instead of request when they're talking about these asynchronous interactions. And while in a lot of cases the practical outcome is the same,
Right.
One service is instructing another to do something.
Yeah.
The word command can sometimes imply a stronger sense of like an imperative.
Okay.
Like it's a directive that the receiving service must obey.
Okay.
Whereas request feels a little bit more like you're asking.
It's softer.
Yeah, it's a bit softer.
It suggests that the receiving service can actually like evaluate the requests
Yeah.
and potentially say no
Exactly.
based on its own rules or its current state.
Yeah, it has the autonomy to decide.
Right. And that's kind of in line with the whole idea of microservices being independent, right?
Absolutely. Each service should ideally have the right to validate incoming requests based on its own business logic and potentially reject them if they're invalid or, can't be fulfilled at that time.
Right.
So while it might seem like a minor semantic difference,
Yeah.
it really does underscore a fundamental principle of microservice architecture,
Yeah.
which is that services should be self-governing.
Right.
They should be responsible for their own data and behavior.
Right.
And that autonomy is actually a key thing that, interviewers often look for an understanding of.
Right. They want to know that you understand that these are independent units.
Exactly.
Okay. So that's a really insightful distinction. And it makes perfect sense in this world of like building independent, resilient services.
Yeah.
Now, thinking about optimizing these service interactions, what happens when a microservice needs to call multiple other services?
Right.
To gather information or to trigger actions.
Yeah.
Is there a way to make that more efficient than just calling them one after the other?
Yeah, definitely.
Okay.
So imagine a scenario where, let's say our order processor needs to get shipping rates
Okay.
for an order from 3 different shipping providers.
Okay.
Now, if it makes those API calls sequentially, waiting for the response from one before initiating the next, the total time for that step is going to be the sum of the latencies of all 3 calls.
Right. You're adding them all up.
Yeah, you're just waiting and waiting and waiting.
But a much more efficient way would be to execute those 3 requests in parallel.
Exactly.
So instead of waiting for like the total duration of all 3 calls added together, you're only waiting for the longest of the 3 to complete.
Right.
Which could be a huge time saver.
Yeah, particularly if one of the shipping providers is really slow.
Right. Yeah.
So the overall latency of the operation is determined by the slowest of those parallel calls.
Exactly.
Not the sum of all of them.
Exactly.
That can lead to some significant performance improvements.
Yeah, it can.
Especially in situations where a microservice needs to, aggregate data from multiple sources.
Yeah, or trigger multiple actions.
Right.
Yeah.
And luckily, there are a lot of modern programming paradigms and technologies that make this easier.
Yeah,
right?
Absolutely.
Like reactive extensions and async await.
Yeah, those are great examples.
Make it much easier to implement this kind of parallel execution and then manage the results.
Yeah, it's a lot easier than it used to be.
Okay, so we've explored these different communication patterns. The direct request response,
right?
Both synchronous and asynchronous flavors.
Yeah.
And then the more loosely coupled asynchronous messaging with the queues and how those can be orchestrated.
Right.
And even optimized for parallel execution.
Yeah.
So I think the big question for anyone designing a microservices architecture, and certainly for anyone answering interview questions about it, is how do you decide which pattern to use in a given situation?
Right. That's the million-dollar question.
What are the factors that guide that decision?
Well, request response is generally a good fit when you absolutely need that immediate result before you can move on to the next step. Or if it's really critical to know immediately if the call has failed, so you can do things like retry it.
Right.
So if you need real-time data or you need immediate feedback, that often points towards a synchronous request response. But on the other hand, asynchronous communication with message queues, that really shines when you need to build more fault-tolerant systems. Improve scalability by letting services work independently, handle those unpredictable traffic loads, even though it might introduce a bit more complexity.
You have to manage state. You have to correlate those responses.
Exactly.
It's almost like a trade-off between immediacy and resilience in a way. It is. Yeah, there are definitely trade-offs to consider. And it's not like these are mutually exclusive options either. In a lot of real-world systems, you'll find a mix of these patterns being used. Like we saw with our order processor example. You might use synchronous request response for those immediate interactions with the warehouse and the payment services. But within a larger business process, that overall might have some asynchronous elements. So the key is to really analyze the specific requirements of each interaction. Think about, do you need immediate consistency? How likely is it that something's going to fail? What kind of load are you expecting? How much coupling are you comfortable with? And then choose the pattern that best balances all of those factors.
And there was one more really important point that you brought up earlier, at the end of our discussion on request response initially, and that was timeout handling. Why is that so crucial in this world of microservice communication?
Timeout handling is absolutely essential in any distributed system. Because when one service makes a request to another, there's always a chance of, network issues, the receiving service being overloaded, or even a complete failure. And without properly configured timeouts, the calling service could end up waiting forever for a response that might never come.
It'll just be stuck.
Exactly. And that can tie up resources like threads. And ultimately, that can lead to cascading failures. And impact the stability and responsiveness of your whole system.
The whole thing can grind to a halt.
Yeah, potentially.
So implementing robust timeout mechanisms for all types of request response interactions.
Both synchronous and asynchronous. That's just essential.
It's not negotiable.
Yeah, it's a non-negotiable part of building resilient microservices.
Okay, so to bring it all together today, we've really taken a deep dive into the core communication patterns for microservices. The direct and immediate request response in both synchronous and asynchronous forms. And then the more loosely coupled asynchronous messaging using those message queues. And we saw how those can be orchestrated to implement those complex business workflows and how they can even be optimized for better performance.
Absolutely.
So for anyone who's prepping for those senior level technical discussions, a solid understanding of these patterns, their trade-offs, when to apply them, that is absolutely critical.
It is.
Because it shows that you understand the fundamental principles behind building scalable and resilient distributed systems. And that's exactly what those interviewers are looking for.
Absolutely.
So on that note, here's a final thought to kind of chew on as you continue your prep. Think about how the specific choice of communication pattern, whether it's a synchronous request that needs an answer right away, or an asynchronous message that can be processed on its own time, how that choice fundamentally shapes not just like the technical implementation and the immediate performance,
Mm-hmm.
but also the broader architectural properties like resilience, scalability, and the overall complexity of managing dependencies between different parts of your system.
Absolutely.
Yeah.
It's a decision with far-reaching consequences. It's not
Yeah.
just a technical detail.
So think about some real-world scenarios you might have encountered or that
Yeah.
you can imagine
Mm.
and really analyze why one approach might not just be slightly better, but like the clearly superior choice.
Yeah.
And be ready to articulate those reasons in your discussions.
Exactly. Be prepared to explain your thinking.
All right. Well, thanks for joining us on this deep dive into microservice communication patterns.
Yeah, thanks for having me.
And we'll catch you next time.
See you later.